Hello, welcome to RF Insights. In this video, I wanted to quickly go over the concept of power flux density, or PFD. Power flux density, or PFD, is a measure of RF energy that is passing through a unit surface area. If you look at this image here on the screen, if there's a point source radiating in all directions, and you move away, at r distance from this source, the amount of RF energy that are passing through this unit surface area can be calculated using by dividing the transmit power over the surface area of the sphere here, right? So if the area here, if the power flux density here is S in this first square here, as you move away from the source at distance 2r, you will have four of these squares, right? 1, 2, 3, 4. In other words, your power flux density is divided by 4. And if you move to the distance 3r, now you have 1, 2, 3, 4, 5, 6, 7, 8, 9 of these squares. Therefore, your power flux density is divided by 9. Or, in other words, we have the inverse square law working here. The power flux density at distance r at the angle theta from a transmitter can be given by this formula, EIRP, or effective isotropic radiated power over 4 pi r square. And EIRP is given by P, transmit power, multiplied by the gain of the antenna in that direction. And the unit of the PFD is watts per square meter per unit bandwidth here. In this case here is 1 megahertz. The power flux density, or PFD, is mostly common in the regulatory documents and regulatory environments. If you're not working in the regulatory environment, you probably don't use it as much in your daily work. But if you're working or dealing with RF regulatory issues, you're dealing with the PFD a lot. So if you convert the PFD to dB from linear to decibels, we will have this formula here. The PFD is EIRP minus the distance and minus 10.99, which I believe is 10 log of 4 pi, right? Now you have the units also changed, dB watt over square meter per megahertz, right? If I want to give you an example of the regulatory literature, for example, if you look at the document SRSP 520, which is produced by the Canadian regulatory body in Innovation, Science and Economic Development Canada, this document explains the technical requirements for fixed and or mobile systems, including flexible use broadband systems in the band 3450 to 3900 megahertz. This one is issued in July 2023. There's a table 2 in that document, if you look at it, that lists some PFD values, PFD trigger values to protect some of the fixed satellite service Earth stations in Canada. This is an example of the PFD used in one regulatory documents. There are a lot of them. I can tell you pretty much all technical documents that are addressing the coexistence of two kind of systems. Normally you can find some PFD values in those documents. Power flux density, you can also calculate it using signal strength at a point in the space, right? In other words, you don't need the radiated power at source to be known in order to calculate the PFD at a distance. If you can measure the signal strength at a point of space, you can convert it to PFD. How? you can use this formula here. So if this is the signal power in dBm or dB watt at a point in space, you can just minus this value from it, and you can calculate the PFD, and the lambda is the wavelength. The unit is dB watts over square meter over megahertz. So it's pretty straightforward and very useful formula to develop the PFD values from signal strength. Here I have an example of signal strength converted to the PFD. You can see the same formula. I've put it in the spreadsheet. So if your wavelength is 0.079 meters, which is 3 gigahertz band pretty much, and your signal bandwidth is 1 megahertz, if you have the dBm values in this column, you can convert them to dB watt, and then you can use the formula in the previous page to calculate the PFD values. So these dBm values corresponds to these PFD values that you see here on the screen. There's another concept that is closely related to PFD. It's called equivalent power flux density, or EPFD, which is very common in the ITR documents. If you're familiar with the ITR radio regulations, the Article 22, for example, which defines the formula for the EPFD, deals only with the EPFD values to protect the geostationary satellite systems. So this snapshot here on this page is from the Article 22. It defines the EPFD with this formula. At first glance it might look a little intimidating, but the truth is it's closely related to PFD. So if you look closely, you will see you have the transmit parameters here. You have the same distance term that you had in the PFD definition here, and you have this receiver gain at direction of the receive over the maximum gain of the receiver, which is a relative gain. This is the only thing that's been added or multiplied by the PFD that we had in the previous formula. So the Article 22 explains that the EPFD is defined as the sum of the power flux densities produced at a geostationary satellite system receive station on the Earth's surface or in the GSO orbit by all the transmitted stations within a non-geostationary satellite system, taking into account the off-axis discrimination of the reference receiving antenna and so on. So here I explained what it means, the previous formula, what it means. Simply is that if you have a receiver with an antenna gain of G and it receives interference from different directions, all of these interference altogether generate an interference power of I at the receiver, right? So this I is the sum of all these interference powers received at the antenna, right? So when these interference values pass through the antenna, we have to include this gain because it's on the way of the signal. Then if you use this I, which already includes the gain of the antenna, to calculate the PFD, it is not a PFD anymore, it is called EPFD. So this side of the formula is exactly the same as the PFD, but this side is not called PFD anymore because it's calculated inside the receiver, not outside the receiver on a point in the space, right? So in other words, EPFD is the same as PFD when it is calculated inside the receiver and it includes the gain of the receiver already. Thank you very much for your attention. Please leave a comment and subscribe. If you have any questions about the topic that we discussed today, please don't hesitate to leave me a comment. I'll try to read all the comments and answer them as soon as I can. Thank you very much and have a good time.